are working with these pennies. So each team of 2 people is going to receive a set of pennies. The year of minting is written on the box, but it's your job, because every year it happens, to check that the minting year is correct. If you have in your box a minting year that is incorrect, bring it back to me and then I will distribute that, okay? Okay, so what we're doing today is the following. First, we're using the analytical balance to take some pennies at the time. We cannot put all of them in the balance because they are very heavy. And we're putting groups of pennies, you need to know how many, in the balance. We tear the balance, we put the pennies, we record all the significant figures. Remember that for the analytical balance, the number sig fig after the decimal point are 4. You need to record all 4 for accuracy of your measurement, okay? So we divide the pennies in portion. We know how many we are putting every time, so 2, 3 portion in the balance. We weigh them. Then we add all the masses of the pennies and divide that number by the entire number of pennies. Okay? What does it mean? That we are going to measure in that way the average mass of 1 penny. Okay? So that's what we are going to do. And we're doing this with analytical balance. Then what we are going to do, the next step, is we are going to use water displacement to perform the measurement of the volume of the pennies. So when we're doing water displacement, we are going to use a 100 milliliter graduate cylinder. We're going to put some water. So here is our graduate cylinder. We are we're using 100 milliliters graduate cylinder. We are going to put some water. We are going to read the meniscus of the water, pointing our eye exactly where the meniscus is. We record this first volume. Then we pour all the pennies in here, and the new volume will be rising to a certain value. Let's say that the new value is going to be here. By subtracting from this value that we are going to read to the third significant figure, this value from this value, we obtain the volume of all the pennies at once. Then we divide again by the number of pennies that we have in each container, okay, in our container, and we obtain the average volume of the pennies. We saw a problem in class in which we were working on water displacement, right? We are doing the same type of calculation. After that, we are going to report, I'm going to prepare an Excel table for the class in which each team is going to write their name, the year of minting, the mass, the volume, and the density that you're going to calculate in grams per milliliter in class for your minting year. Okay? Then I will collect all this value and email it to you so that you can make 3 graphs. One in which you have the mass versus minting year. One in which you are representing the volume in milliliters, this is in grams, versus meeting here, and one in which you're representing the density versus meeting here. Okay? So you're obtaining in your post-lab calculation 3 grams. You have to comment on the accuracy and precision of the overall measurement from the class, because it could be that in theory the mass should be always like this, no changing in theory, or maybe there is a change, we don't know, but you need to see, is the mass consistent? Do we have accuracy, so it's close to true value, and precision? Or do we have values that are like this? So we have systematic error, or what is the other type of error? Random error, correct. Same thing for the volume, same thing for the density, okay? So you don't have to mention the name of the people that might have made a mistake, right? But you have to mention what is the meeting here, where if somebody did the measurement wrongly. In your conclusion, you have to report what is the source of error, what could be the source of error, what could be the source of error in your measurement of the mass, for example. What could it be? Not closing the doors of the balance. Another error?
Putting too many.
What's that?
Putting too many.
Putting too many. Another error? Carlos?
Not tearing the balance.
Forgetting to?
Tear the balance.
To tear the balance. Third source of error. For the volume, what could it be the source of error? Not feeling?
Yeah, just say like you added 60 millimeters of time and
So you're saying no filling with the initial water, the granite cylinder? I wouldn't say so, because you're doing this only once. You're filling the granite cylinder with certain amount of water. You add the pennies and you read it. That's it. It's only one measurement. Okay? Because all the pennies will fit in the granite cylinder. So it's a one-time measurement. No, what is another source of error? I have an I here. I'm going to put another I here. What could be the source of error?
I guess measuring the wrong one, or
Right. We don't read accurately the volume. This is a very common error. This is one of the most common error, number one. Number two, we might not read the correct number of significant figures. Remember that when we are making measurement, there are a certain number of figures. They are called certain, because we can actually read those. You have to read to the first uncertain figure. And that is done by, you remember we said that we take the granite cylinder and we have the volume of the water that is, for example, here at this mark, and between these 2 points we divide the volume, the space in 10 parts. You remember? We talked about that in class. So 2, 4, 6, 8, 10. And we leave to the interpretation of you, operators, to determine what is the last sig fig. This variable, okay? So make sure that you know how many certain figures, significant figures, you have in your volumetric, in your graded cylinder, and then I leave to your interpretation the last one. So oftentimes a problem that we have in this lab is that students don't use the correct number sig fig, and so they lose in accuracy information. Okay?
So for this experiment, we're going to be determining the density of a penny for a particular minting year. Because of the amount of pennies, we're unable to do all of them at once. So we're going to divide them into 3 batches. For each batch, we're going to record the number of pennies, and then after that, we're going to weigh the mass of each batch of pennies in grams using the analytical balance to the number of significant figures. Once we have the total mass of pennies for a minting year, we're going to divide the total mass by the total number of pennies to figure out the average mass of 1 penny. To record the mass of all the pennies of the minting year, we split them into 3 batches. So first we're going to turn on the analytical balance, and making sure that all doors are properly closed for an accurate and precise measurement, we're going to tare it, and then we're going to insert the empty vial of the penny casing, close the doors, and then we're going to tare the balance again. Now that it's tared, we're going to put the first batch of the 1979 pennies, which has a total of 19 pennies. There are 19 pennies, and we're going to place them back into the analytical balance, and we're going to record the mass in the proper number of significant figures. Once this is recorded, we're going to take out these pennies and put the second batch of the same year. In this batch, there will be 20 pennies. We're going to place this vial back, close the door properly, and then we're going to record the amount of mass for this batch of pennies to the proper number of significant figures. Now for the last batch of the 1979 pennies will be another 20 pennies. And we're going to place this back in here, close it, and record the amount of mass in proper number of significant figures. After recording, close it and turn it off. For the 2013 minting year, we're going to be recording the mass. So first we're going to turn on the balance. We're going to place the empty vial inside, make sure all the doors are closed, and then we're going to tare the analytical balance. After it's tared, we're going to put the first batch of 17 pennies of the 2013 minting year. Close it. And then we're going to record the amount of mass in proper significant figures. Now we're going to take out and place the second batch, which is 20 pennies total. Record to the proper number of significant figures. This is the final batch of pennies. It will also be 20 total pennies of the 2013 minting year. Record. Out. The second part of this experiment is to find the average volume of 1 penny for a minting year. So for this, we're going to be using the water displacement method, using a 100 milliliter graduated cylinder. First, we're going to add water to the 100 milliliter graduated cylinder, and we're going to record that initial reading. Once we've had that and recorded it to the appropriate amount of significant figures, we're going to add all of the pennies of that minting year to the graduated cylinder, and we're going to record that final reading to the appropriate amount of significant figures as well. Using these two readings, we can calculate the volume of the pennies of that minting year, and to find the average volume, we're going to divide that by the total number of pennies used, and once we've had the average volume of 1 penny, we can use that to calculate the density of pennies for that minting year. First, we're going to add some water to the 100 milliliter graduated cylinder for the 1979 pennies. So this is the initial volume of water for the 1979 batch that we're going to record to the appropriate amount of significant figures. We're going to add all of the 1979 pennies to the graduated cylinder. And we're going to tip the graduated cylinder to prevent any loss of water. This is the final reading of the water and pennies for the 1979 year. So record to the appropriate amount of significant figures to find the final volume of pennies. Once you've recorded the volume, we're going to dump out all the water from the graduated cylinder. And we're going to pat these pennies dry. After these pennies are dry, and by patting the pennies, we're going to take away as much of the water as possible to put them back into the until their vial casing. For the 2013 minting year batch of pennies, we're going to be adding some water to the graduated cylinder. This is the initial reading of the volume of water in the graduated cylinder for the 2013 pennies. So record to the appropriate amount of significant figures. We're going to add all of the 2013 pennies to the graduated cylinder. This is the final reading of the water and pennies for the 2013 minting year. Once you've recorded the appropriate amount of the volume to the appropriate amount of significant figures, we're going to calculate the average volume of 1 penny. To find the average volume of 1 penny, you're going to divide the volume obtained by the pennies by the total number of pennies. Once you've recorded the volume, we're going to dump out all the water from the graduated cylinder, and we're going to pat these pennies dry. After these pennies are dry, and by patting the pennies, we're going to take away as much of the water as possible to put them back into the until their vial casing.
After we're done collecting all our data, you are supposed to have your own data for the mass, the volume, and the density of one penny for 2 minting years. And then I will provide on Canvas the following information: the other team minting year, average masses, average volume, and average density. What you will need to do with this data is to calculate accuracy and precision of the class data using the Appendix E. And then you have to write your conclusion regarding the data collected. You prepare 3 graphs in which you're going to report first the minting year versus the average mass versus the minting year, and see if there is a change in the trend of the mass over the years. Then the average volume versus the minting year, and then the average density versus the minting year. If there are any outliers in the data that you're reporting, please comment on those. Calculate the average of the mass, volume, and density for all the years, and determine the accuracy and precision using Appendix E. Appendix E is located in Files, under Lab Material, Statistical Data Analysis. In order to calculate the accuracy, you will use the average, and then you will calculate the experimental values minus the true values. So for you will be your own value minus the average value of the class divided by the average value of the class, and your errors should be below 2%. And for the accuracy, what you're going to do is you're going to calculate the relative range. You're going from the highest value of volume, for example, minus the lowest volume of volume divided by the average volume, and determine if the class was accurate. If your error is below 2% or equal to 2%, that means that the class are operating in a precise mode, way. They were precise.